Okay, welcome to your lesson on transforming trigonometric functions, a very big idea in math and science. We're going to take some notes on the worksheet. Let's begin with the top here. We're going to mark the period and amplitude on both the sine wave, which looks like this, and the cosine wave. So first, to figure out the amplitude, I'm going to think about that first. Amplitude basically means the height of the waves, but we don't mean the full height, we mean the height from the center line. So here's the center line, right? It's like above that is the same distance as below. So this is called that center line. And then if you look at the height there, that's called the amplitude. So in this case, the amplitude is 1 because the height of the wave is 1. And then down here, it's 1 to the negative as well. And it will keep going forever, and the height is always 1. That's called the amplitude. The period is how long it takes to complete one full wave. So for example, if I start here, and I go like that, follow the curve, here at 2 pi, I'm back at the beginning. So that's like one rotation around the circle. So the period is just how long it takes to complete the full cycle. So there's one period, and the period in this case is 2 pi, because it takes 2 pi to complete that. And you know that from the unit circle. You go once around, it's 2 pi. So there's your period. Let's do the same thing on the cosine wave. On the cosine wave, I'm going to do the center line again. I'm going to look at how tall the waves are. That wave is, has a height of 1. Therefore, the amplitude is 1. And the period works the same way. If we say we begin here at 0, we go down, up, and back to that upper point. So we've gone back to here. So it took 2 pi to complete that whole cycle, and that is a period of 2 pi. Okay, great. Let's look at all the different transformations you've learned before for functions and apply them to sine and cosine waves. So let's, for every one we do, we're going to compare to a parabola, because a parabola is a good one to kind of see what the basics look like. So this is a basic parabola. However, the vertex is over here. It's not at 0, 0. So even though the parent is this, I'm going to call the parent, oh, there it is, the parent y equals x minus 2 squared, because that's how you get the parabola there. This is the true parent, but in this case, we'll say this is the parent, and then we're going to apply a rule to it in order for this function to do what it says here. So to reflect this over the y-axis, so over this axis, we're going to have to flip it this way. That means all the x values here have to turn negative because it has to end up here. So the rule for that is we take the function and we make the x values negative, as shown here. Now we're going to apply this rule and write what the function looks like. So if the x's become negative, then this x will become negative. And there's our child function. Right? If you were to graph that on Desmos or your GDC, you'd notice this one looks like this, and then this one, now the x has been made negative. That means all the x values become negative over here, and the graph ends up being over here. So that is a reflection over the y-axis, and it's done doing this rule. We're going to try this now for the sine curve, I believe. Yes, let's look at this one. Is this the sine or the cosine? Well, the parent, it begins at 0, and that must be the sine, because the sine wave always begins at 0 there. Now the rule, again, we're reflecting over the y-axis. The rule is the same as we saw. We make all the x values negative, or the opposite of what they are, and now flip it over the y-axis. So then the child will be sine of negative x. That x becomes negative. Now if you were to check that on Desmos or GDC, you would notice you get a graph that flips over the y-axis. However, have the amplitude and period changed? Well, all we've done is flipped it over the y-axis. So the amplitude, the height of the waves is still the same. So the amplitude is still 1. And the period, well, we haven't compressed the wave at all. So it still takes 2 pi to complete one period. The period remains the same. All we've done is really flipped it. So here is the graph of the flipped one. I'm going to go back and forth for a second. See this one here? It goes from 0 and goes up. Now if we flip it over the y, it's going to go from 0 and up in the negative direction like that. And that's exactly what we have here. It's going this way now, and on this side, it's going this way. So after sketching that in, take a close look and think about that, how it flipped over the y-axis. Okay, next one, reflection over the x-axis. That means it's going to be a flip up and down, right? From here, down to below. So if this is your parent function, the parabola, the rule for flipping over the x-axis, if you remember, we need to take all the y values, which are positive up here, and make all the y values negative, because we're trying to make it flip down like that. So instead of making the x negative, we're going to make the y values negative, which means the whole function becomes negative. Alright, so that's the rule for reflection over the x-axis. And if you apply that rule, then this becomes negative x squared. The negative is applied to this whole function. And that ends up looking like this, reflected over the x-axis. Now let's apply that to trig function. So here we have this one. Which wave is this? Well, here's 0. It begins at 1. That means it must be a cosine curve. All right, the rule, we're going to flip it over the x-axis, is that rule. To flip it over the x, we make all the y values or the entire function negative. So there's the rule. Now the child is going to be negative cosine of x. The negative is applied to the whole function. And now we're just flipping it again. So the amplitude and the period remain the same because all we did is flip it. There's no crushing or compressing of the wave or stretching it. So it's still going to have a height of 1 and a period of 2 pi. Let's see what the graph looks like. So now imagine this flipping upside down this way. So if this begins here and it flips upside down, it's going to begin down here, right? Let's take a look. Oh, sorry, this one's showing you a little bit into the negative, but it's the same curves here. Here's 0, and it began here at -1 and it went up here like that. All right, so flipped over that axis. Sketch that in, and then let's look at the next one. Now we have a vertical stretch or compression. Vertical means up and down, right? So when we're stretching up and down, we're affecting y values. And here it says sketch each curve vertically, stretch the curve vertically by a factor of 2. That means vertically we're stretching the y values by 2. We're making it 2 bigger on the y. So here's your parent. The rule to do this kind of stretch is to multiply the entire function, which represents the y values, to multiply it by 2. So it's going to stretch all the y values 2 times higher. So the child is going to look like this, 2x squared. All right, let's see what that looks like. So imagine that. Imagine, for example, this point here. This point is at 1, 1. And if it's stretched vertically, that means the x value remained the same, but the y value is going to be 2 times bigger. So now instead of at 1, 1, that point should be at 1, 2. So let's take a look at the graph. And there it is. That 1, 1 point is now at 1, 2. So the y has been stretched vertically times 2. And you'll do that for every point. For example, here's 2. On the original, this is a 0.24. On the new one, it would be 2.8. So off this graph here. But there it is. Let's try that with this. This is a sine curve because it begins at 0. So for this one, it's important to note this will affect the amplitude. So think about that. If you're stretching this one up and down, a vertical stretch, it's going to make it 2 times taller, which means it's affecting the height, which is the amplitude. So let's take a look. The parent is the sine graph because it begins at 0. Here it is, the sine wave. The rule to stretch it vertically is to do 2 times the function. So we're doing the same stretch of 2, so we're going to do 2 times f of x. The child then is going to be 2 sine x because we're doing 2 times the function. And now if you graph it, see I've graphed the sine, and now instead of here on the original it went up to 1 and down to -1, now it goes up all the way to 2 and down all the way to -2. So it's twice as tall basically, right? So the amplitude is 2 now, from the middle to the top is 2, the height of 2. And the period is still 2 pi because we haven't changed how long it takes to complete that cycle, right? So here it goes up, down, and comes back to the starting point, and that took 2 pi to accomplish that. So that hasn't changed, just the amplitude has changed. And here is just to demonstrate that. I put the center line in, and the amplitude is now 2. So remember that, it's the vertical stretch that changes the amplitude. That number in front is the amplitude. Great, now we're going to look at horizontal stretch or compression. Horizontally compress each curve by a factor of a half. Now this one you got to remember the rules about horizontal stretches or compressions. Let's think about this carefully. Horizontally compress. It's telling us it's going to crush it, not stretch it, but compress. Crush the curve by a factor of a half. It's going to be half as wide as it used to be because horizontally means a change along the x, so it's going to be half as wide. So here's your original. The rule for this is one that's often confused, but now we're changing the x because we're doing a horizontal adjustment, but we put a 2 here. Even though this says a half, we put a 2 here. It's always the reciprocal. All right? So even though we're going to make it half the size, it has a 2 here. That means that rule applied to this one will be 2x squared. Make sure you see that this one is different than the last one. The 2x is in the parentheses, because if you put just a 2 on the outside and then x squared, it would mean it's affecting the whole function. But here we're affecting only the x, 2x. And that curve will look like that. All right, so the original is the green one, and the new one is the orange one that you're going to add to your graph. Notice, for example, we have a point here at 1, 1, and we've made the x values half of what they were. So now 1, 1, y value stays the same, but x value is now 0.5, 1. Let's look at another point. On the original, we had a 0.24. Now the x value is half of what it was, so the x value is 1, and the y value is still 4. So it got compressed by a factor of half. Half is y. All right, let's try that with the sine cosine. I see a cosine curve because it begins at 1. It's important to note that what we're doing now, this horizontal compression or stretch, affects the period, because now think about it. If you're compressing this side to side or stretching it side to side along the x or horizontally, it's going to change how wide that curve is. So let's take a look. Our parent is the cosine function. This is cosine. The rule is we're going to do a compression, so we put 2x there. So now we do cosine of 2x, that's inside with the x. And that's going to make this one half as wide as it once was. So now, take a look at that. And now if we make it half as wide, look at how there's more waves in that same amount of space, right? So it's been crushed or compressed sideways. So now, if you look at here, in the beginning, let's look at the beginning one, cosine goes from 1 to pi over 2, then pi, all right, to go from top to bottom. But now, from top to bottom, if it's going to be half of that, it's going to do all the top to bottom movement all the way to pi over 2. Let's take a look. So it goes here, crosses at pi over 4 instead of pi over 2, and ends at pi over 2. And then, likewise, if you keep going all the way to the end, back to the beginning point right here, occurs at pi. It used to be, it has to go all the way to 2 pi to get to the end of one period, or one cycle. But in this case, now it does that in half the time. So as you get to pi, it's already done one cycle, or one period is done. All right, it's been compressed. So the amplitude is still 1, because we haven't changed how tall it is, but we've changed it how wide it is on the x, so the period has changed. The period is now pi. It used to take 2 pi to complete one cycle, now it takes pi to complete one cycle. All right, great. Just one more. Horizontal translation. Translate the function 1 unit left. Horizontal translation. All right, so translations are the ones where you just move it around. Here's our parent. Here's the rule when you're translating horizontally. Horizontally, again, affects the x values. And if we're moving 1 left, remember these x ones, we always do the opposite. Instead of going -1, we go +1. So apply that to your function, you get this, and graph it. There it is. All right, so the orange one is a new one. It's moved over 1 unit this way. Even though it says +1, it's moved -1. Horizontal translation. Let's try with sine cosine. With a sine cosine, if we want to move it over, and it says translate the function pi units right. So we're going to take this whole thing and move it to the right by pi. We're going to use the same rule. Our parent is the sine in this case. The rule is we want to translate horizontally, so we're going to change the x values. It says 1 right. I should have put minus there. So this should say minus. All right, ignore that. Let me make that change right now. Minus, all right. Let's make sure, okay, change this one as well. All right, let's try this again. So there's the original. I'm moving it pi units right, so this should be minus pi here. That means the child function, the sine, is minus pi, and the amplitude is going to change or not. Let's take a look. So first of all, let's move the curve. Here's the minus pi. So this point, for example, is now at pi, but if you move everything to the right pi, that point will be at 2 pi. Or this point is at 0, and if you move everything to the right pi unit, so this 0, 0 point will now be over here. So let's see if that's what happens. Yeah, that's exactly what happened. All right. So this point, just the whole curve moved pi units to the right. And when you graph them together, you can see it more clearly. But basically, yeah, again, think about this point moving over all the way to here. And there it is. So it's like it begins here and it goes up and down from there. So There it is, it moved over. And this, by the way, is called a phase shift. When you move it side to side, it's called a phase shift for these curves. The amplitude is still 1, still has a height of 1. The period is still 2 pi. We just moved it, but we haven't squeezed or compressed the function or stretched it. All right, let's look at vertical translation. Now we're moving up and down. Vertical is up and down. Translate the function 1 unit up. All right, 1 unit up. Sure. So 1 unit up would mean we're changing the y values. So the rule for that is you're taking the whole function with these y values and you're adding 1. So rewrite that as x squared plus 1. And that will become this. If the whole one moved up to the orange one here, it moved up 1 unit. Let's try with this sine or cosine curve. This is a cosine curve. The parent is cosine because it begins here. The rule is we want to move it 1 unit down. So we're going to do the function minus 1 to move it down. The child is going to be the function minus 1 then, so cosine x minus 1. So this whole curve should remain the same, except it's all going to be shifted down. So now think about this point here. It's going to begin here, isn't it? All right, and this goes all the way down to negative 1. Well, if everything's shifted down 1, then this is going to be down here. Let's take a look. There it is. It's exactly the same curve, but everything has shifted down 1. All right, it's just gone down 1. So the amplitude remains the same, because now this negative 1 is actually now your middle line. So let's go back to here. Here, remember, your middle line is at 0 here. But now in the new one, the middle line is here. And the amplitude is still 1. Just the whole curve is moved down. And the period is still 2 pi. We haven't compressed or stretched. We've just moved where it is. Great. With all that information, put it all together now into all these rules. So now you see this function a, b, c, d. It has all those things we just looked at all in one function here. This, to help us out with the kind of work we're going to do, you can rewrite it. I see a b here, but I see here. So it's easier if you factor out the b in here, actually, because it's going to make it easier to see what's going on. So I'm factoring out the b. That means this must be x plus something, all right? So if I'm factoring a b out of here, that must mean that this is c over b, all right? Think about that. Multiply this b back in here, and the b back in here, and end up with that. So here's what I get when I factor out the b. This is going to help us figure out what the amplitude and everything is. First of all, remember, amplitude is how tall the wave is, and the number in front was the one that told us what the amplitude was. Look back on the example with the amplitude change. It has the number in front is the one that affects it. That's the one that's the vertical stretch. So the amplitude is always going to be that value in front, the a. The period, all right, the period is determined by this one here, which is a horizontal stretch or compression. That number tells us all about the period. So just to consider a couple of things, let me write something here. We have sine, imagine we had an example of sine 2x. That's the one that was compressed to half its width, all right? So that one you compress to half its size, right? That 2 becomes a half when you're compressing. Think about this one now here, if you had sine of bx. So if this one means half the size, then this one means 1 over b compression, 1 over b, right? Just like that, like that. So now 1 over b. So that means normally a period of a sine function is 2 pi. 2 pi is the normal period. But now we have this number in front, so the period is going to be 2 pi times 1 over b, which is 2 pi over b. All right. For example, again, this one, the period of a normal sine function is 2 pi, but when we have that 2 there, the period is half its size, and the period becomes pi over 2 pi, which is the normal period divided by 2, which is just pi. All right, so this makes the period become pi from 2 pi. So the rule for that is this: you take your period, a normal period of 2 pi, divide by that value there, and it'll tell you what the new period is. So that's how you find the period of anyone. Phase shift, that's the one, the horizontal translation, moving it side to side, left and right. And the phase shift can be found by this number here, right? But in this case, we factored this out, so this is the phase shift right here, c over b. Or negative, it's always the reverse of that, right? And finally, the vertical shift, just moving it up or down, the d tells us how it moves up and down. So these are kind of the rules you have to be able to use. This is kind of abstract with all these letters, so let's try one here. You see this function here. I'll help you with the first step, and you try the rest, see how you do. So first of all the rules have been applied here. We have numbers everywhere. I'm going to take this, I'm going to factor out the 2, just like we did in that last one. So I'm going to rewrite it exactly as it is, but the 2 now, I factored it out. And if I factor out a 2, I get x plus pi over 4 here. Okay, minus 1. So now look at each of these individually and figure out which one's which. Which of these is the amplitude? Which of these tells us what the period, or use that little formula to get the period? Which one is the phase shift and the vertical shift? All right, a couple of those are really easy. A couple of them take a little more. Think about, you can do it. Let me know if you need some support.